Hi everyone, welcome back to the Heterogeneous Parallel Programming class. We are at lecture 2.5, Memory, Model, and Locality, and we're going to be focusing on tiled matrix multiplication. The objective of this lecture is for you to understand a basic tiled parallel algorithm for matrix multiplication. We're going to be learning how to load a tile into shared memory, how do we partition the execution into phases, and how we can use barrier synchronization to enforce phase execution. Matrix multiplication is a very important application in science and engineering domains. That's the reason why over the years, many people have worked on the optimization and parallelization techniques for matrix multiplication. It's also simple enough for us to fully understand all the trade-offs involved. Once we understand matrix multiplication for tiled algorithms, then we can actually move on to learn about tiling for more complicated applications and situations. Here is the basic concept of tiled matrix multiplication. So what we can do is we can first identify all the data that we need to do in order to generate a tile of output elements. So for every output element, we're going to need to have a row of A and a column of B. So if we just look at all the rows involved in generating the elements in this output tile, then we have a strip of rows in A, and we also have a strip of columns in B that are needed to generate all the elements of C. So here I show the strip of A and B, the strip of A and strip of B that should be involved. So here we show all the columns of B in this vertical strip. So this identifies all the data of A and B that will be needed to generate this tile of C. So when we design a tiled algorithm, what we can do is we can divide up the execution into phases. And then we can actually focus on a small portion of that strip of A and a small portion of the strip of B during every phase of the execution. So this is going to be the basis of our algorithm in this lecture. As we have divided up the strips into tiles, then we can begin to learn how to load a tile into the shared memory. So in CUDA, a very common approach is for all the threads in a thread block to participate. So if we divide up the strips of A and B into tiles of equal size of the C tile that we're generating, then it's very easy to design our loading mechanism, because we can just use exactly the same thread that is calculating a particular location. So let's say this particular thread is calculating this element. Then we can have the same thread to load the corresponding relative position of A and B that I'm showing here with the blue dot in the loading process. So because if we design the tiles of A and B to be the same size as the C tile, then we can just use every thread that to load exactly the same relative position of the A and B elements in the input tiles. And this is a very simple design, and as it turned out, that is also a very effective design. So once we assign the elements in the relative position, then we can actually come back and look at how effective that method is in terms of the memory system performance. And as it turned out, that this simple assignment also gives us extremely good memory access performance because of a phenomenon called coalescing. And we're going to come back to this point next week. So this is a simple, small example that illustrates the loading of tiles and the phase execution in our algorithm. So we have a very simple matrix. We have a 4 by 4 of A, 4 by 4 of B, and we will generate a 4 by 4 of C. And we're also going to divide up all the thread into 2 by 2 thread blocks. And in order to process generate the entire C array, we're going to have 2 by 2 grids. So in this particular situation, we have each tile of C to have 4 elements, 2 by 2. So when we divide up the A and B arrays, we know that in order to generate the upper left corner tile of C, we need to have the upper half of A and the left half of B to be for all the input data we need. So we can go ahead and divide up the process into 2 phases. The first phase will use the upper left corner of A and the upper left corner of B to generate partial values for all the elements in the upper left corner of C. So this will be essentially the phase 0 execution of all the threads in thread block 0, 0. And thread block 0, 0 consists of all the threads that will be processing the upper left corner of C. So what we can do is we can have every thread that is responsible for generating the C elements in the upper left corner to also load the same relative position element of A and B. So for example, thread 0, 0 is going to be generating C, 0, 0. And during the phased execution, we're also going to have thread 0, 0 to load A, 0, 0 and B, 0, 0 into the shared memory. And same thing with, let's say, thread 1, 1. Thread 1, 1 is going to be generating C element 1, 1. So during the loading process, we're also going to have that thread to load A element 1, 1 and B element 1, 1. So this simple correspondence gives us a very, very systematic and simple way of coordinating the loading of elements into the shared memory. So this picture now shows how the loading of A and B tiles into the shared memory works. So during the before the zeros phase, we will have all the 4 threads to load the 4 A elements into the shared memory, and we're also going to have all the 4 threads to load the 4 B elements into the shared memory, and these are pre-declared arrays in the shared memory. Once we have loaded all the 4 A elements and all the 4 B elements of the first of the tiles into the shared memory, then all the threads will do a phase of the inner product calculation out of the shared memory. So we're going to have essentially let's say thread 0, 0 is going to need to use the zeroth row and the zeroth column of zeroth row of A and zeroth column of B to do that dot product. And if we look at the shared memory has now half of the elements of A and half of the elements of B that this particular thread needs to use to generate the final dot product for element C00. So we would do the first phase of execution by having each thread to use the elements that we have already loaded into the shared memory for the first half of the dot product. So we're still going to use a for loop, and this is the iteration 0 of the loop, where all the threads are going to be generating the first dot product, the first multiplication for that first step of the dot product. So for example, thread 00 is going to use A00 and the B00 to generate the first multiplication and accumulate step for the dot product. And thread 01 is going to be using A01 and B01 to generate the first multiplication and accumulate result. So as we can see, during this iteration 0 of the dot product, every element that we loaded from the global memory is going to be used by 2 threads. So then we will just so every thread is going to is going to generate 1 step of the dot product out of the entire computation. Now we can move on to the iteration 1 of the for loop. So when we go to iteration 1, all the threads will be using the second element in their sequence. So thread 00 now is going to be moving to to A01 and then B10. So we can make the same argument for other threads. For example, thread 11 is going to be using A11 and B11 to generate 1 more step of C11. And so as we can see again, during this iteration, all the threads are going to be using a pair of elements A and B in the shared memory, and every A element and every B element in the shared memory will be used by 2 threads. So this completes the execution of phase 0. Once we completed the execution of phase 0, we can move on to phase 1. And we will now need to move to load another tile of A, another tile of B into the shared memory. Since we have already used all the elements in the shared memory in the previous phase, we can now overwrite those elements in the shared memory. So when we bring the next tile into shared memory, we can just overwrite the previous tile loaded from the previous phase. So now we're loading A02, A03, A12, and A13 into the shared memory. And we're doing the same thing for B, but we're loading B20, B21, B30, and B31 into the shared memory. So essentially, we're loading the second half of the A strip and the second half of the B strip in order to calculate the upper left corner of the C matrix. So once we have finished loading, we can now consume all the elements from the shared memory. So now all the threads will be doing the second phase of the inner product calculation, and the iteration 0 of the for loop in this case will be consuming the A02 and A12 and B20 and then B21 for all the threads. As you can see that again, all the elements, each element is going to be used by 2 threads, and so they're used 2 times. And then we can move on to the next step. So this is iteration 1 now. Next slide, please. And we're going to be consuming B30, B31, and A03 and A13. So again, for all the elements, every element is going to be used by 2 times by 2. That is by 2 threads. So this completes the execution of the second phase. So at the end of the second phase, every thread has used up 4 elements in this example, and every C element is now complete with the dot product result. And in the process, we load every global memory location once into the shared memory, but we use that same data twice out of the shared memory. So we cut down the memory traffic by 50% using this 2 by 2 tile configuration. And in the previous slide, we talked about phase execution. And we say that, once all the threads finish loading a tile, then they can go ahead and consume the elements from the shared memory. And then we say once all the threads completed their calculation based on the shared memory, they can go ahead and move and load the next tile from global memory into shared memory and overwrite the contents of the shared memory. And this requires coordination. Something has to make sure that all the activities have ended in the previous phase and before you can start the next phase. And this is accomplished in parallel computing with barrier synchronization. Barrier synchronization is a very important primitive for parallel computing for exactly the reason that I have just discussed before. And in real life, barrier synchronization is also very frequently used. For example, you can imagine, let's say if 4 of the roommates in a dorm want to go shopping. So they take the same car to the shopping mall. And then, before they split, they will say, okay, we're going to each go to a different store and do our shopping. But let's come back here, let's say at 4 o'clock, so that we can all go back to the dorm. So the barrier synchronization happens around 4 o'clock where all the roommates come back, and then you need to make sure that all the 4 roommates have finished shopping and in the car before you leave. So if one of the roommates is late, then the barrier synchronization will make sure that the other 3 roommates wait for that roommate so that they don't leave without him or her, right? So this barrier synchronization is very important to coordinate activities when everyone needs to be on board before you can do the next phase. So in CUDA, barrier synchronization is provided as an API function, and the name is SYNCThreads, __ SYNCThreads. This is a function call that gets mapped into a machine level instruction that does barrier synchronization. When the threads execute this instruction, the semantics is such that any thread that executes this instruction will begin to wait for everyone else to also reach that point. So if any thread has not reached that point, then all the threads who have already reached that point will be waiting until the last thread reaches that point. And then all the threads will be allowed to continue their execution to the next phase. So this is used in tiled algorithms to ensure that all the elements of a tile have already been loaded. So we have all the threads to collaborate and load the data tile data into the shared memory. And we use barrier synchronization to make sure that all the threads will have finished, because the threads may execute in slightly different timing. So some of the threads may be delayed, and some of the threads may actually move ahead faster. So we use a barrier synchronization to make sure that even though each thread may take different amount of time to load their elements, they have all finished loading the elements before any of them can begin to consume the data from the shared memory. And then the barrier synchronization also will be used to ensure that all the elements of a tile in the shared memory have been consumed. And then before you will go up and load the next batch of elements and override the contents. The reason is if any thread still needs to consume more elements in the shared memory, you really don't want to have other threads to potentially overwrite that content. So this picture is what I would like you to remember in your head about barrier synchronization. So here we show that there are n threads, thread 0 through n-1, and they all execute some kind of activity in different amount of time. Some threads may take shorter amount of time to finish. Sometimes threads may take longer amount of time to finish. So this is the point where we have the last thread to finish. And when they execute the barrier synchronization, even though these threads reach that synchronization point at different times, but they all have to wait until the very last thread to reach the point, and then all the threads will be released from the barrier so that they can all do the next phase. And this brings up a very important caution that I would like to make. Whenever we execute a sync thread or barrier synchronization in general, all the threads in a block will be waiting for each other. So if we have a thread that will take much longer than others, we can have a situation where the most of the threads in a block are not doing anything. They're waiting on the barrier. So we can actually significantly reduce the number of active threads in a block when we execute the barrier synchronization. This is one of the reasons why we will want to have multiple thread blocks executing in an SN whenever we execute a tiled algorithm, because some of the thread blocks may be doing barrier synchronization and they may not be able to utilize the hardware resources while waiting for the last thread to finish. So this is the situation where having other thread blocks in the SM will help us to make better use of the hardware resources. And this, we'll come back to this point later. So at this point, you have already have all the basic concepts you need in order to understand a tiled matrix multiplication kernel in CUDA. So if you'd like to learn more about the tiled matrix multiplication algorithm, I'd like to encourage you to read the textbook section 5.4. Thank you.